Hey everybody, welcome back. Mr. G here. Today what we're going to do is an example of solving a Thevenin's equivalent circuit. So using Thevenin's theorem. So just as a review, you can find Thevenin's theorem, chapter 8-5 of our textbook. There's also a procedure that you can follow, which you'll find in your lesson notes from Blackboard. And I'll walk you through the procedure that I'm going to do here for this circuit. So basically what we're going to do is we're going to take this circuit. We have 1, 2, 3, 4, 5 resistors and a load. So what we're going to do is we're going to Thevenize this circuit and turn it into this. So we have to calculate V Thevenin and R Thevenin. And I'm going to walk through the procedure, walk through the calculations with you. So in the end, we end up with Thevenin's equivalent circuit. So, before I begin, I'm going to suggest that you pause the video right now and you try this yourself. And then we'll come back and I'll show you my solution. So again, I suggest that you pause the video, so pause it now. Hey, welcome back. Hopefully you had a good time working out this Thevenin's example. So now what we're going to see is if your answers match my answers. So what we're going to do is I'm going to walk through solving this circuit so we end up with Thevenin's. So we're going to solve for Thevenin's equivalent resistance first. It does not matter which you do first, whether you do Thevenin's equivalent resistance or Thevenin's equivalent voltage. They are two completely separate calculations. They have nothing to do with each other, so it doesn't matter which one you actually do first. So here's what we're going to do. I'm going to walk step by step to do Thevenin's resistance, and then we'll come back and do Thevenin's voltage, and then we will put the two numbers back into our Thevenin's circuit and end off at that point. So again, we're going to walk through the procedure. So the procedure that is on the line, and the one that you follow in the book, your first step is to remove the load. So what we're going to do is I'm going to recreate this circuit. So this is a 1K here, this is a 2K here. There's a 3K, 4K, 5K, and then this is where the load was. So we remove the load, so that's our first thing we do. Then in the notes, I suggest you mark it A and B. The next thing you have to do is you have to short out the power supply. So what you're going to do is you're going to take the power supply and just put a line through it like this and pretend it's not even there. So we've shorted out the power supply. Now, if looking back this way we find the resistance from point A to point B, that is equal to Thevenin's resistance for that circuit. So what we need to do is we need to figure out what the resistance is of this circuit. When I look at that circuit from point A to point B, what I see is a 5K resistor in parallel with a 4K resistor in parallel with this branch. So that's 1K plus 2K plus 3K. So this becomes the resistance from A to B, and that resistance is Thevenin's equivalent. So we're going to solve this down, so that ends up being 5K in parallel with 4K in parallel with 1 plus 2 plus 3 is 6K. Again, that is what we end up with. So we're going to plug those numbers into the calculator. So we're going to go, there's our 5,000, 1 over, plus 4,000, 1 over, plus 6,000, 1 over, equals 1 over. So what I get for this number is 1.62 kiloohms. So 1.62 kiloohms, that is our AB, which is our Thevenin for this circuit. Okay, so again, we remove the load, marked it AB, short out the power supply, find the resistance from A to B. So if I put these resistors in this configuration and I put an ohm meter here, what would it read? So if I actually built that circuit and put an ohm meter here, what would it read? So my calculation says we got 5K in parallel with 4K in parallel with this branch, which is 6K. Now I know that my answer could possibly be correct because when you have 5K in parallel with 4K in parallel with 6K and you come up with 1.62K, this number must be smaller than any of those individuals. If you come out with a bigger number here than any of these, then that must be incorrect if these are in parallel. So our Thevenin for this particular circuit comes out to be 1.62K. So I'm going to put that right here in my circuit, 1.62 kiloohms. So now we need to calculate Thevenin's voltage for this circuit. So what I'm going to do is I will just draw a line here. Calculate V Thevenin. So the first thing we need to do is when we are doing V Thevenin is go back to the original circuit. So we're going back to this original circuit. And then we follow the procedure that we have for calculating V Thevenin. And the first thing is remove RL, so remove the load. So again, from that circuit, I'm going down to this. So this is the 1K, this is the 2K, here's the 3K, 4K, and 5K. This was 12 volts. This is where the load resistor was. We've removed it. We're going to mark it A and B. Now, if I built this circuit, the voltage that I read from A to B on a voltmeter, that would be Thevenin's equivalent voltage. So now what I've got to do is I've got to figure out where I find that voltage in that circuit. And if you look carefully, you can see that point A is here and point B is here. So the voltage AB appears across the 5K or the 4K. So these things are in parallel, so the voltage across the 4K is the same as the voltage across the 5K, which is the voltage that we require, VAB. So now what we have to do is we have to solve the circuit and find the voltage across one of those. Doesn't matter which one, it's going to be the same, so we'll just pick the 5K. So the voltage A to B in this case is the voltage across R5, which is that 5K resistor. So now we have to solve for that. So the easiest thing to do is to come up with an equivalent circuit of this so that we can figure it all out. So what we have, so we can figure our total, is we have this in series with this, in series with this, in series with these two in parallel. So what that works out to be is our total of this circuit is equal to 1K plus 2K plus 3K plus 4K in parallel with 5K. So when we do 4K in parallel with 5K, since there's two resistors in parallel, we can do the product over sum. So 4,000 times 5,000 equals divided by 4,000 plus 5,000 equals. So this works out to be 2.22K plus 3K plus 2K plus 1K. So our total in this is 1 plus 2 plus 3 plus 2.2. So that is 6,788.22 kilo ohm. So that's our total. So we want to find the voltage across from point A to B, which is across R5 or R4. There's a few ways we can do that. Now that we have this value here, we can actually use our voltage divider and figure it out. Or if we wanted to, we could use Ohm's Law, so calculate the current and then figure out how much current is flowing through each of these resistors, okay, and do it all. I find in this particular case the easiest way to do it, so the voltage from point A to B is from here to here. So that is represented by that 2.2K resistor right here. So the voltage A to B is equal to the total supply, which is 12 volts. And you'll recognize this as our voltage divider. So the voltage divider, our total of the whole thing was 8.22K, and we want to know 2.22K. So we've got this little part of the whole thing is equal to the voltage, this little part of the whole thing. So it's a ratio thing. So let's do that calculation. 222, so 2.2K divided by 8.22K equals times 12 equals. So 3.24 volts. So 3.24 volts. Again, there are many different ways that you could solve this. You could actually find, again, I total and then look at the voltage drops. So you've got Kirchhoff's voltage law for series circuit, where all of the individual voltage drops must add up to the total. So you could do it that way. I chose to do it voltage divider. You could use Ohm's law, whatever way you want. So the voltage from A to B calculates to 3.24 volts. That is actually Thevenin's voltage. So we bring back our original circuit. V Thevenin is 3.24 volts. 3.24 volts. Now, if you remember, the way that Thevenin's works, or the reason for Thevenin, it's equivalent circuit with respect to the load. So that means in the original circuit, if I looked at the current flowing through that or the voltage drop across that, it should match the current flowing through here and the voltage drop across. So we can do a little bit of proof if we wanted to. So in Thevenin's, we can actually find the current through the load real easy. IRL is equal to, it's the series circuit, so it's actually equal to I total of that circuit, which happens to be 3.24, which is our voltage, divided by our total resistance. Whoa, I made a mistake here. This goes here, 1.62K. This value is just our 1K. Sorry about that. So that becomes 2.62K. So 3.24 volts divided by 2.62 kiloohms should give us our total current. So we do 3.24 divided by 2.62 exponent 3 equals. So the current going through that resistor is 1.23 milliamps. So again, this is our load value resistors, that's 1K. So if we took 1.23 milliamps multiplied by 1K, the voltage across RL is the current going through it. So in this case it's I total times 1K, so that's RL. So that's 1.23 milliamps times 1 kilo ohm. The voltage is 1.23 volts. So the current going through there is 1.23 milliamps. The voltage drop across is 1.23 volts. In order for this to be true, I must get the same calculations on this circuit. So on this circuit, what I'm going to do is I am going to figure out R total of that whole circuit, and then I'm going to try and figure out what current is going to be flowing through here or what voltage is going to be across this whole network, and they should match. So R total in this circuit is 1K plus 2K plus 3K plus 4K in parallel with 5K in parallel with 1K. So this is in parallel and all in series with that. So 4K in parallel, 5K in parallel with 1K. We'll figure that out. So 4,000 plus 5,000 plus 1,000 equals, so 690 ohms. So this thing works out to be 690 ohms plus 3K plus 2K plus 1K equals our total. So that's 1, 3, 6. So 6.69 kiloohms is our total. So if we wanted to, these three resistors equate to that value. So we can use the voltage divider and we can look at it like this. So voltage divider, the voltage across RL is equal to 12 volts, 690 ohms over 6.69 kilo ohms. So the voltage across RL should be 690 divided by 6.69 exponent to the 3 equals, and then times 12 volts. 1.23 volts. 1.23 volts. Looky here. I now have that voltage. I can find the current. Ohm's law says that the current through RL is equal to the voltage across RL divided by RL. So that becomes 1.23 volts divided by 1,000 ohms equals 1.23 milliamps. Looky there. So, those values jive. They work. We've proven that the current and the voltage in this circuit with respect to that load is the same as the current and voltage in this circuit with respect to that load. So, here's the procedure. R Thevenin, V Thevenin, our calculations, and our proof that it actually works. That is Thevenin's equivalent circuit. That is the original. I hope this helps. Everybody take care. We'll see you again next time.